And here we see the gorilla sapien in their natural habitat, a college campus. Observe as they scour the campus for food to nourish their overworked bodies.
Today we'll be surveying these crickets' breathing rates for certain temperatures in order to relate it to activation energy. By putting the natural log of the breathing rate into the Arrhenius equation, we will be able to calculate the activation energy of these crickets.
Alright, so temperature? 285 Kelvin.
And chirps? 4,632.
Alright, temperature? 293 Kelvin.
And chirps? 7,800.
And temperature? 295 Kelvin.
Chirp, 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 chirp,
And
chirp,
number
chirp,
chirps?
chirp, 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 chirp,
8,900. Cool. Thanks.
So this is our video on the chemistry behind cricket chirping. Through field study, crickets showed signs of chirping more at particular temperatures and less at others. This hinted at activation energy for the crickets, which is the lowest energy they chirp at any time. The cricket's activation energy can be seen as an indicator of the mechanisms within the cricket and is synonymous with how chemicals respond, only after a particular energy is reached. In order to find this, several steps must be taken.
This image shows the relationship between temperature versus chirps per minute. The chirps per minute can be seen as a rate constant because they state the amount per time. However, the chirps must be given in chirps per second. Multiplying the chirps by 60 will give proper rate constant.
And the table on the left shows the data that was given within the graph. From this data, we can determine ln k and 1 over t. We simply find the natural log of each of the chirps per second, and we find 1 divided by each of the temperatures before giving the graph of ln k versus 1 over t. The slope of this graph multiplied by the gas constant will be the activation energy, because when the equation is rearranged to form ln k over 1 over t equals negative EA over R, then the EA over R will be an indicator for the slope in an equation similar to y equals mx plus b. This means that the activation energy is equal to the negative gas constant times the slope. The graph on the right shows the data that we received in the ln k versus 1 over t. This information was then graphed to form the line needed to find the activation energy.
Right, so how all these factors relate can be demonstrated by the Arrhenius equation. So determining the activation energy of a living being is similar to how one would find the activation energy of a chemical. By rearranging the Arrhenius equation, as given here, the activation can be determined with the temperature, the rate constant, and the gas constant. K represents the rate constant, EA is activation energy, R is the gas constant, T is the temperature, and A is the frequency factor. The frequency factor in this case does not need to be represented because it is the y-intercept of the line the equation makes.
So in finding the activation energy, this graph shows the linear relationship between the natural log of the rate constant and temperature. Using the data, we can follow the equation change in y over change in x. This equation makes the slope negative 5,756.876. From this point, we multiplied the negative gas constant of negative 8.314. This will give us the activation energy of the cricket's chirping.
When finding the activation energy for the cricket's chirps, finding the temperature in kelvins and the number of chirps per second helped give the data to put into the Arrhenius equation. By multiplying the slope of the ln(k) versus 1/t graph with the known gas constant, we were able to determine the activation energy, or the lowest energy possible for the crickets to be able to chirp.